As we continue our exploration of XR technologies, our next session focuses on critical aspect of immersive systems, calibration for XR devices, covering its importance, challenges, and methods. It is my privilege to invite Ms. Hema Sathiamurthy, architect at Samsung R&D Institute, India, to present calibration for XR devices, importance, challenges, and methods. Ms. Hema brings rich experience from her previous roles at Continental and Robert Bosch Engineering and Business Solutions and holds a master's degree in communication systems from IIT Madras. May I now request Ms. Hema Sathiamurthy to take the stage for this session.
Good evening, everyone. Myself, Hema. So today we will look upon one of the very critical but overlooked part of XR. Hello, is it okay? Yeah. So we will look at one of the very critical but overlooked part of XR devices, which is nothing but calibration. So the topic for today is calibration for XR devices, importance, challenges, and methods. So I'll start my talk with a very small video. So this video is actually showing us how the immersive experience looks like. So you see that there is a real world, and along with that, there are virtual objects also which are placed. And along with that, there is also an integration of the audio. Yeah, so the first question, what is calibration? So we saw that how the virtual world was completely immersed in the real environment. So now the calibration is the part that is helping us to process how we align these two worlds actually. So there are various sensors that are involved in XR devices. We have cameras which are going to track your head, your hand, your eye, and then we have the depth cameras which are going to give you the perception of the depth, and then we have this IMUs. There are face tracking cameras. I think in the previous session we saw about all these cameras and then how they work. So now the calibration is actually telling us the intrinsic components or the parameters of these sensors. Like for example, if you take camera, then what is the focal length, the principal point, and based on the lens, it also gives you the distortion parameters. And when it comes to IMUs, which has this gyrometers, accelerometers, so it gives us the bias, the scale term, and also for the different things, like for example, the pass-through cameras, so it tells us how the stereo cameras should work together, how are they aligned actually. So along with this intrinsic parameters, this alignment also becomes very important. So for a perception functions, now they know there are various sensors that are placed. We know what are the intrinsic parameters of the sensors, and along with that, we also know how each of the sensors are placed on this device. So this is what calibration is actually going to help you with. Now, let's see why is this calibration so important in XR devices? So calibration needs to be very accurate actually. Any small mistake or any small wrong parameter, it could happen because it was not calibrated well, or let's say it was calibrated perfectly, but because of some issues, the sensors itself got disoriented. Then we will have very small, minor issues, maybe in terms of millimeters, but that actually affects the way user perceives the things. So the tracking might get lost. You won't be able to track your head, or let's say for a user, he's trying to touch upon something, but it's actually pointing at something else, or the depth perception gets lost. You won't be able to perceive the depth properly or reduce immersion. And because of this, the biological balance within the human body gets altered, which leads to motion sickness, visual discomforts, or headache. So calibration actually that way is very critical for XR devices. Now let's see what are the parameters that we are calibrating. As I mentioned, for the cameras, the focal length, principal point, the distortion parameters, and IMUs, we have this accelerometer, gyrometer. For magnetometer, we also calculate this hard iron, soft iron parameters. But the important point is not just finding out these parameters, but the time alignment between these parameters. Because in XR devices, all these sensors work together to give you this immersive experience. So time alignment, the spatial alignment is also very important. And calibration will also ensure that, like for example, a user is using it. So the distance between the two eyes, which we call it as IPD, it might vary between various users. So we need to ensure that it fits perfectly for a user. So to ensure that, we actually like calculate something called as IPD, and based on that, we also need to do the color calibration and the display calibration. So color calibration in the sense, we need to ensure that whatever is there in the real world also matches with what you see through the device. Now let's say, what are the important calibration technique? So let's assume that XR device is getting manufactured in a factory. So as soon as it's out from the factory, we do something called factory calibration. So in factory calibration, you have a very confined setup where you will do this calibration, where like for example cameras, you have the proper calibration targets like Chariku markers or like checkerboard, and we have the very specific movement of these devices. So it's a proper setup where we do this factory calibration, and all the parameters like what I mentioned about the intrinsics, extrinsic get calculated. Now, you have the device that was calibrated in the factory, it gets shipped. So because of the shipping, or it could be because of the drop, again this calibration changes. So we see the second part of it, which is nothing but the user calibration. So once the user wears the device, we actually like expect the user to do the calibration, like in the sense like we will ask him to perform a few functions actually. So based on this, we will again be doing the calibration. Here is where we do this IPD adjustment or the comfort settings, or we also try to see how his hand looks like actually. The next part of it is actually a very important one. So even after we do all this, we expect the calibration to change. And this is very specifically for XR devices, because the XR devices are very flexible actually. So there is a calibration which is called as online calibration, which keeps happening continuously in the device. But user will not be involved in this actually, like in the sense like there is an algorithm that is always running in the device, but user need not intervene and like select anything actually. So this is called online calibration. Here we will take care of this sensor compensation, the real-time adjustment. So these are the various types of calibration. Now let's just look at how the online calibration is performed actually. So because like I mentioned, so this is a calibration that becomes very specific for the XR devices, very important part of the calibration. So there are quite a few techniques, quite a few SOTA techniques. However, the mostly used techniques will be the extended Kalman filter and then VIO, which is nothing but visual inertial odometry. So I'll just touch upon these algorithms. Like in extended Kalman filter, what happens is the calibration parameters becomes your state variable, and there are two steps here: prediction step and the update step. In the prediction step, the model actually tries to predict what are the parameters, and in the update step, we actually measure these parameters and try to compare whatever was predicted is actually same as what we measured. So that way, like it keeps calibrating in an iterative manner. So that is about the extended Kalman filter. We have another thing called VIO, which here it works based on the fusion of the IMU parameters, which will be running at a very high frequency, and the camera data actually. So the camera data, though it's at a low frequency, it's going to be a very accurate information. So based on this, so we will fuse the two data and we will try to see how the IMU values might be shifted or drifted over time actually. So though like we are mentioning that there is this online calibration, we are using a lot of methods, it's still an open challenge actually, like open problem that needs to be solved, because this online calibration that I'm mentioning might not work at various different conditions, like for example, like very low light, or like let's say the device has actually like it has fallen down and there is a very big orientation error with respect to the sensors, or it could also be during the travel where your IMU and the camera data might be giving different information. So this is still an open problem that we are trying to solve like continuously. So Yeah, so with this, I would like to end the talk regarding this calibration. I also have my colleague Chinmay, who is going to explain about one of the use case in XR devices.
Thank you, Hema. So what is forwarded rendering? And so forwarded rendering is a very important optimization technique that is being used to improve the performance. So how does it improve the performance? So it helps to reduce the power consumption by reducing the computation that is happening where your eye is focusing. So it is motivated by a human eye. So you can see there is a human eye. So human eye normally has only 20 degrees of foveal region where it can focus, and rest all the regions is periphery, where it is there, but you don't have much of your interest area there. So you can see that the eye gaze, the famous eye gaze based foveation, which has already been explained by Dr. Anup, where in the foveal region you have very much high resolution in fovea. You have very peripheral region where you have low resolution in peripheral region, and there is a medium resolution area where there is a blending that happens. So most of the computation in XR device or Galaxy XR happens for the foveal region, but whereas in the peripheral region, the computations are very less because the human eye actually cannot see. So you must have seen Apple Vision Pro demo videos where you see that people tell about there is a fovea, the images are blurred outside. So the user who is wearing it cannot feel it, but if you capture those things, you can experience, okay, there is a foveation happening on the device. So in where exactly this foveation happens and whatever calibration parameters we have seen. So the calibration parameters is being used by various methods for, like, for example, it is used for generating the 3D reconstruction. It is used for getting the position of the device where the person is looking at the head position, and all those informations are being used by this graphics pipeline, where if you see in the graphics pipeline from the vertex shader till primitive assembly, all the geometrical operations happen. The 3D reconstruction models are loaded, the head pointing direction is taken, a volume frustum is created, the objects that are the mesh points of vertices which are relevant are kept into the volume frustum, and those details are geometrically processed, and rasterizer creates a 2D plane. So that 2D plane, after that 2D plane is created, there is lot many operations that happen on an XR device. That is, it takes care of the lighting, it takes care of what is the exact resolution you're looking at, and in this process is very costly process. That is the process where actual, that is happening in fragment shader, and it is the most expensive process that is happening. So this is in fragment shader, we see that most of this foveated rendering algorithms go in place where they are trying to, based on the eye gaze data which is there, they try to perform maximum computation only in the foveal region, but the outside area is very low resolution area, and finally there is a processing unit after you generate this foveal outputs and the background outputs, and both the outputs are overlaid on each other. That is what is the famous core view foveation, where you can see that there is a low foveation, there is a background image that is being generated, and there is a foveal region, very small foveal region that is generated. So where you are seeing that time, you will have lots of detail, and at the final, what the user actually sees, it's a complete scene where the fovea region is properly having all the details, but the background region is having very less details. But the user cannot feel it. He has the full experience. You are saving on the power, and you are actually having higher frame rates, which reduces the motion sickness. So this is one of the application of foveated rendering using the camera calibration parameters. Thank you.
We thank Ms. Hema Sathiamurthy and Mr. Chinmaya for a highly informative session.